I'm Kevin. So yeah, I suppose just today what we're going to look at today is just some work that's been on in the community for the past year, particularly around memory management and the new modeling we've introduced there. And then specifically, we're going to go through some debugging aspects as well, so hope people find this of use. So just a quick overview of the content that we're going to look at. So we're going to start off, if you're familiar with DPDK, you might roll your eyes here and say, well, you know what an mbuff and a mempool is, but I suppose some people here may not have used it. So it's actually quite useful to just give a high-level overview of what's involved with mbuffs and mempools, which are a core concept of memory anyway for DPDK, in particular what we'll be looking at today. We look at the default kind of memory model we used to have, which was or still have, but what was in there in the past, shared memory overview. Then we look at the new introduction we brought in this year, the per port memory model. Then we'll take a look at the memory model support to date between the releases, and then finally, just some topics for conversation, maybe in breakout sessions, but just future memory models and modifications we can do in around that. So I suppose, at a very high level, what's an mbuff? And what you have is actually an mbuff is just an RT mbuff struct. And within this struct, it has metadata about the actual packet data that's being encapsulated in the mbuff. And so this big blue segment would represent the total length of the mbuff. You have an mbuff struct just at the beginning, which would have data as where does the packet data start, what's its length. It'll have information about the headroom and tailroom. So you might wonder, well, what's that for? Well, the mbuffs themselves are cache aligned for performance reasons. And they can either be a single encompassed mbuff, or as you kind of saw with Tiago's presentation there, you could also have multiple segments. So an mbuff actually referencing the next mbuff in the pool. And that brings us on to the next part. Well, where do mbuffs exist? Well, they exist in a mempool. And what does that look like? So this was kind of borrowed from the DPDK documentation, but the core aspect here is on the right-hand side, you have a list of objects, and these are actual mbuffs, and they all live in the mempool. I've included the idea of having a core on the left-hand side, so you can see core 0, OVS DPDK, and a reference to an object cache there. That's kind of important because if you have multiple cores on the system and they're all using this one shared mempool, well, that could be performance penalties involved there, and how do you handle that? So there's actually this concept of having an object cache for that core, which is referencing free mempools, essentially. And as well as that, below that, you'll have an RT ring, and that's the idea at the bottom there, is just to store memory pool of pool-free objects. And, we won't dive too deep into this, but just the idea here that you need to take away is that you have a membuff, it's inside a mempool, and that the core can actually interact with them via either its object cache and the RT ring store. So if we were to kind of go forward then and say, well, what's in OVS DPDK previously? What was the model we were using? We had this idea of the shared memory model. And it was basic, but it worked well for what we needed. So if we take an example system, we have two sockets. You can see that we have NUMA memory allocated on each socket. And then we have our OVS bridge, which we'll be using to add ports and interfaces into OVS DPDK with. And the idea, how you figure it out would be if you want to share the memory pools, how would that be done? It's done on two attributes. So it'll be done on the socket ID that the port is actually connected to, and the MTU size being configured on the actual interface itself. And so it's just, if we were to build up an example, you might start off and we might have a physical port on socket 0, and we're just going to leave with a default MTU of 1500. So that will be allocated on socket 0 from the NUMA memory pool there. Let's say we decide to add a second port. So it'd be DPDK port 1, but the bus slot function in this case would be attached to socket 1. So we can't share the mempool. You see, we have to create a new mempool on the memory for socket 1. Even though the MTU sizes are the same, it's different sockets. If we went forward and we create, say, vhost user port, something like that, so we're creating a virtual port on socket 0. In this case, yes, the socket IDs match, they can be shared, and the MTU sizes are both 1500. That's okay, they can both be reused. But if we were to create another virtual port, in this case, we'll say that the socket is 0, but we give it a configuration of an MTU of 9000. In this case, no, the size of the mpuffs might be affected here. The mempool will have to be a different mempool. And so this is just a high-level overview of how the previous model worked. And I suppose when we looked at this, it's like, well, what are the benefits and what would be the drawbacks? So benefits are, I think this has been in place since about OVS 2.5 at least. So it's a mature solution. It's pretty well tested and has been bug fixed over the past number of releases. And I suppose another really good point would be it can have a very small memory footprint for the same socket and MTU config. So you saw there whether it was physical or virtual ports, they could use the same mempool. And that could be n number of ports essentially. We also have the idea of over-provisioning because we're using the same mempool. You have to set over-provision the number of mbuffs, but we account for that by doing some calculations and just providing for what we think will be the worst in-flight case. The drawback, however, could be that if you have two ports and they're using the same mempool, the configuration of a device on one of those mempools could affect the other and essentially just exhaust it. And so this is a real case on the right-hand side that I have here. It was an actual mail-on discussion list. And essentially, right, they had one socket system, they had two DPDK ports. When they were running things with just one RxQ on both ports, that was fine. They were using an MTU 1500, no problem. But then they said they configured 64 queues on the first DPDK port. That was still fine. Then they decided to use 64 RxQs on the second DPDK port, and at this stage they got an error. And it was actually because it actually couldn't allocate the memory. The configuration had just drained the mempool at this point. And so this was kind of back to us in the OVS community of, well, you know, it was back to essentially how we were provisioning for it, and how would you get around this problem. Now, it's kind of a corner case, and it's very rarely came up, but, you know, it still was an issue that had to be resolved. So the discussion went around and said, well, you know, why don't we just do a per port implementation and just isolate the memory pools from one another? And so in this case, you know, this referencing back to the previous example I gave, use your two-socket system, and you can see DPDK0 has its own memory pool, VOS0, VOS1, and DPDK1. They're not sharing a mempool anymore. So regardless, essentially, of the sockets or MTUs or anything like that, it's never shared. Just you have your own memory. So, okay. What would be the benefit of that? I suppose, well, it's more transparent would be one good thing. So if you're doing some debugging, you can kind of be sure, well, at least, you know, this memory pool is primarily in use by one port, and so I can kind of debug and help along with issues there. That's okay. It avoided the memory pool exhaustion issue that we saw earlier, and that's good. But the drawback was actually that the memory footprint was complicated at this point. It was even more complicated than that was before. We kind of had to move away from this idea of having a general over-provision. We had to start making it more specific to the device configuration itself. So it starts taking into account, rather than just socket and MTU, it now takes into account things as how many RX and TX queues you have configured on the device. What's the RX and TX queue size? What's the number of PMDs will have an effect on that also. So from a deployment point of view, you have to have a more technical understanding of the knowledge in terms of what's going on with the memory underneath. It's not as, you know, fire and forget model anymore. It can have a real impact. And what was a bit more nuanced, which only became, I think, apparent later in the release, was that the memory requirements can change for given deployment between two OVS releases. And this could be a blocking factor for anybody using OVS DPDK. So what we mean by that is if we took our shared mempool model and our per port mempool, and we put them side by side, okay, the single socket system again, if we just said, right, we have one physical port and n number of vHost ports on the left, socket 0, they're all using MTU 1500, and it's all one PMD, one RxQ, that's fine. You could budget essentially, look, the new memory footprint for this would be, you'd have to require 788 megabytes essentially. I'm not going to go into the calculations of that right now. Kevin's going to do that in a few slides, but you can actually just do some provisioning right. So for my system, if I want this n number of the virtual interfaces, which is one physical interface, which is discussed as that was kind of a typical deployment, they could use just 788 MB, and that could be okay because you may not have huge in-flight numbers of traffic. You may just have many interfaces but low volume. That would work fine. If you were to go to your per port mempool, as we said earlier, now that memory has to be allocated regardless. So you need to be aware of when you're going to be using that. So you have to start doing this calculation at an earlier stage. And in this case, if you were to stick to using the 788 megabytes, well, I think when we roughly made this out, it would come out at roughly, let's say, with 78 megabytes, and you have 10 interfaces, so you might get one DPDK port and 9 or 10 vHost ports in around that. I actually think it was about 68 megabytes. And so you get about 11 interfaces there before you'd hit this upper limit of 788. So that may not be a problem for you. You might say, no, that's still okay. I still prefer the isolation. But let's say we decide, okay, well, let's increase the number of PMDs and the RxQs. So in our shared memory model, your footprint would probably just be the same. You don't have to really allocate anything more. But on our right-hand side, as we said, the algorithm for allocating memory changed. So now the number of PMDs and the number of RxQs are taken into consideration. So we've went from being 788 to 880 megabytes. Now you might need to think of, as we said, if we go to 4 PMDs and 4 RxQs, now you might have to start budgeting for over a gigabyte, 1,115 megabytes. So that really could be a blocker moving between deployments essentially for customers, because memory at the end of the day is a finite resource. They may not be in a position just to hand out extra or budget for that. So with the idea of that being, we kind of put on hold, I think it was around OVS 2.9, we held back from putting the per port memory model into that release, and we decided, look, OVS 2.5 and 2.9 would just be shared memory model use, so anything between those releases and including, use the default shared memory. But for 2.10, we were going to do a bit of work and just make sure both models would play nicely together and that you could use both without being blocking for customer upgrading. And so what we found was that what we decided on was that OVS 2.10, by default, uses the shared memory model. So any customer upgrading will just be a clear update, but that you can enable per port memory if required. And so just the option there would be vskettle other config per port memory is equal to true. We had to do this because, again, we did have users in community on both sides. Some people preferred port model and some people didn't. So it's something you have to provide both for. I suppose then just building on top of that, future memory models. 1805 has kind of introduced the idea of the reworked DPDK memory model. It can have cool things like hotplug capabilities, and you can specify things such as min and max of your memory now being provisioned for your application. So I'm wondering, is there something kind of cool we can do there, some bit more fine granular controls around the memory? And ideally, when we move into using 1811, that should start being available generally on master. We can start looking at that. Another really interesting concept that came from our friends at Ericsson during the conversation of per port versus shared was, does it need to be at the interface level? Maybe the PMD is in a better position to make these judgments, and there's some credit to that. The PMD has the idea of the number of RxKs it's using. It has an idea of utilization, so it can definitely figure out, are we hitting the worst case in-flight and non-flight kind of cases? But that would be a bigger memory design rework, so then we'd still have to make sure that, we're not introducing another problem on the other side. But that could be two potential areas that we could look at in the future. So at this stage, I'm going to hand over to Kevin.
Okay, thanks, Ian. So that's fine, but I guess the basic question we got a lot of the time is, okay, whatever about these different memory models, how much memory do I need to give it as a user? And it's a very difficult question to answer because it goes right down through the code to determine how much you need. So just some of the factors that would be needed for this. If you think about the shared mempool models, there's obviously the MTUs and there's the NUMA of the ports. So as Ian showed, depending on whether they can share MTUs or ports are on the same NUMA node, depends on whether we can actually share those mempools between ports. For the per port mempools, it's even more complicated. So it depends on the number of RX queues, it depends on the number of TX queues, and how many people have set the TX queues for OVS DPDK? Good, because it's derived from the number of PMDs, so there isn't a setting for it. So it's PMDs plus 1, so that's completely non-obvious to a user. Also then the size of the RX queues and the TX queues, because we need to put a mempool for each of these entries in the queue. Then for both of those models, there's the metadata that Ian showed at the start of the MBUF. And there's also some more stuff. There's rounding, and I guess there's maybe we need space for VLAN tags, and then as we go down through the stack into DPDK, there's maybe rounding for alignment and maybe more efficient memory access. So it's kind of very difficult, I would say, bordering on impossible to get a really accurate calculation. So the best thing to do is just estimate and then test your scenario with the kind of ports, the number of ports, the number of queues that you're going to use. Okay, so just as kind of an example of how you do an estimation for a shared mempool. So we know the mempools are kind of based around, size of the mempools are based around the MTUs and the NUMA models, and that decides whether we can share them or not. So for example, if we had ports on 2 NUMA nodes with a 9K MTU, when we add in metadata and some rounding per buffer, that goes to about 10K. For the initial mempool that we try and get, it's 256K buffers in that mempool. So if we multiply it out, it's 2.7 gigs per NUMA node. Now, I know that's quite a lot, but if that's not available, it'll retry for smaller mempools. So obviously we can't change the buffer size because the MTU is the MTU until we have something like single segment or multi-segment MBUFs, but we can make a smaller mempool. Okay, so that brings us to kind of some of the kind of things that you'll hit, maybe debugging that you might see. So there's kind of three, I think, areas. So the first is init. So I think this is the kind of red face one that if you hit this, don't tell anybody. So it's just basic kind of config. So the first thing is we can set the DPDK socket memory through the OVS DB, and that filters down directly into DPDK. So in this case, we say 4096 on NUMA 0 and 4096 on NUMA 1. So that's 4 gig on NUMA 0, 4 gig on NUMA 1. The first thing, of course, we can hit is the huge pages aren't mounted. And we can see that it gives us a perfectly kind of readable debug to tell us exactly that. There's 32 1 gig huge pages reserved, but they're not mounted. And also a good tip is in the logs, and the line above that, where it says EAL args, it shows the arguments that we pass down on DPDK initialization. So we can be sure that 4096 actually went down. Okay, so then another thing is we might try and look for too much memory, and again we get a perfectly kind of readable debug that will tell us there's not enough memory available. Okay, so I don't think these are too common, but they can happen, and you can't see them there, but there's a couple of links at the bottom in the OVS documentation that will kind of explain about using that OVS DPDK socket mem entry, and also about setting up huge pages. Okay, so this is probably the most common one, I would say. If you hit an issue with running out of memory, this is probably going to be here. So adding a port, changing an MTU, starting a VM, what all these have in common is they may require you to create a mempool. So obviously if you're using per port mempools, you probably will need it. But if you're using shared mempools, you may be able to reuse an existing mempool. But you may not, so you might create one. For adding a port, I guess the port needs a mempool. We need to fill the RX queues with mbuffs. For changing MTU, as we saw from Diego and Ian, the mbuff is so long, but if we can't fit the new MTU in it, we need to get a new mempool with new mbuffs. And starting a VM is kind of the least obvious one, but what can happen is when a VM starts, DPDK will look at where the memory from the guest is allocated, which NUMA node it's on, and things will kind of realign in DPDK and OVS to try and be on the same NUMA node. So in that case, we may create a new mempool to align with the memory from the VM. And so in that case, there can be a new mempool created, which of course can lead to a failure. So the first entry there is may need to retry for smaller mempools. So this is actually a DPDK message saying we cannot reserve memory. And it's kind of where we get into the layering between OVS and then DPDK. So from a DPDK perspective, a mempool has been requested of a certain size, and it maybe can't honor that. So it's perfectly acceptable. It would say, there's an error, we can't reserve that memory. But from an OVS application point of view, we can look at the eno mem error, and we can retry for a smaller amount. So if you see that, it's fine, but I guess just maybe an indicator for later on that you didn't get all the membuffs you wanted, but you should be still operational. Of course, eventually, we don't retry forever. We retry for so much, and eventually, you might not be able to get the memory, and in which case, you get a message from netdev DPDK, so this is directly from OVS, and it'll say we failed to create a mempool. So that's going to be a problem for you. If you're adding a port, the port won't be operational. That's not going to work because you can't fill the received descriptors. If you're changing MTU, it'll fall back to the previous MTU. Okay, so pools of buffers exhausted. So as Ian mentioned in one of his slides, you can get into a scenario where you actually got the mempool you wanted at the start, but then you actually exhaust the buffers from it. So I think it's worth putting this here, but really I think it's kind of an unrealistic use case, because like Ian showed about having 64 RX queues. So if you want 64 RX queues from the NIC, presumably it means you want to process the packets from them in parallel, which means you want 64 cores for your vSwitching. So I think for 2018 anyway, that's probably unrealistic. And I think I had to hack the code to make this happen, but so with excessive ports and queues and descriptor lengths, you can maybe exhaust the mempool. So there's a couple of error messages here. One where a 10 gig NIC couldn't allocate some more buffers, and one where vhost couldn't. And of course, if you're in that scenario where you want to run with lots of ports and lots of queues and the big descriptor lengths, really you should use the per port mempool model. The other alternative would be to try and reduce some of those RX queues. I mean, you probably don't want to get rid of ports, but you may be able to reduce the number of RX queues or reduce the descriptor lengths on them. Okay, so last one. So there's some debug. If you turn on debug in the file or syslog, I suppose there's nothing like trying to debug some memory issues to get the right logs in. And now I think the logs are pretty good. So if you're creating ports and starting VMs and changing MTUs, every time a mempool is allocated, every time a mempool is reused, every time a mempool is freed, will be logged. So that's a nice way that you can kind of, as a user, do the actions you want to do and see what's happening as it goes along. From a more static point of view, there's also a command to see what mempool every port is using. And I put that in SOS log as well. So SOS report. So if you run SOS report, you'll get a list of all the ports and what mempools they're using. There's kind of a code to the name of the mempool. So OVS mempool 2030 was the buffer size, 0 is the NUMA node, and then 262.144 is 256K, the amount of buffers in the mempool. And that's it. Oh, hi.
All right, let's thank our speakers. I think we have time for one question.
So maybe my understanding was wrong, but I thought there was a floating relationship between PMDs and the ports they serve. We kind of like have ability to look at what's not loaded and move them around. Like, how does that work with the memory pool? Like, if things moved out, especially to across.
I didn't catch the question. Could you?
Oh, so I thought there was a way to have a floating relationship between the PMDs and the ports they serve, as far as the scheduling goes, right? Yeah.
So so you're talking about.
So if the PMD, this PMD here on this NUMA node decided to serve this other port based on the load, right?
Yeah, so that's there as well, but it's kind of almost a separate thing. I guess the mempools shouldn't change because, for the shared memory model, it's only based on MTU and it's based on NUMA node. But the core that's used to poll that queue would also be based on the NUMA node as well. So you wouldn't like balance things or change things around where a core from a different NUMA node was trying to poll a port from a different NUMA node. That's kept in place.
Okay.
I think if you use purport memory pool as a single producer, single consumer, right? But if you use shared memory pool for many ports, it will be multi-consumer, multi-producers, right? It will result in lock contention.
No, so do you want to answer this?
I think it's the TX batching, is that kind of what we're getting to here when you're TXing a packet?
I think you're talking about the mempool itself, about the multi-consumer. So the DPDK mempools are set up as multi-consumer, multi-producer.
Yeah.
And they use atomics, but they're lockless.
Yeah. So I think if we use a shared memory pool, it will impact our performance.
I don't think so.
See any?
I don't think so. No.
Because memory pool is multi-consumers and multi-producers. Right?
Sure, but there's no like strict locking. It's just done on atomics. And the other thing you have to remember is that there's caching, as Ian showed, for the different cores. So probably all the time you look, you'll just be going to the local cache.
It looks like that was our last question. Let's thank our speakers again.